the implications of nanoscaled and quantum-based devices and their applications in real systems. Because in reality, before quantum devices are going to become prevalent in any significant fashion, they're going to have to find a way to interact with our microelectronic kind of framework that's already in place. And so I will talk a little bit in general at the beginning about what some of the various types of devices that have been considered, and obviously looking at what has already been covered in the conference. But later then I'll focus a little bit on some of my own work looking at single electron transistors and some work that we've done in that area really over the last 3 years only. So we saw earlier in the conference, I forget which speaker it was that presented it, but was looking at the technology integration that's basically documented by Moore's law and the expansion of the scaling of our technologies, as well as the reduction in size, feature sizes that have allowed that migration to take place. That's basically represented by this red curve on this graph. As we see, currently production is at 65 nanometers. I mean, at 300 millimeter substrates, they are producing 65 nanometer features, which is a remarkable technological feat. This is being done primarily by Intel, but it's being done also by companies like NEC, by IBM Corporation, by Texas Instruments, by a very wide host of companies in the field, Samsung as well. And what was recently announced, actually about it, I'm trying to think of how long ago it was the demonstration, the full demonstration of 45 nanometer technologies. This is actually real gate lengths in these devices. Now, when we start talking about dimensions that are in 40 nanometers and smaller, we're talking about devices that definitely are reaching quantum limits, and yet they are still pushing existing technologies to these levels. So the question might be asked, what's going to happen to these quantum-based devices if the trends continue to the ultimate limit that we see with silicon-based FET devices, where the quantum effects tend to take dominance at about 10 nanometers. We see that the nanotechnology and the nanoscale devices, which are basically using quantum effects, or basically using things like nanowires, nanorods, nanotubes, we see the progression in size happening at a more rapid pace, but where these two might merge and how these two very different types of devices may work together, it's not absolutely clear yet whether quantum-based devices are going to easily be integrable with microscale FETs or submicron FETs. So one of the key technologies that limits this is the ability to produce features at these dimensions, and that has been one of the main pressures on the semiconductor industry and on the the industry that supplies equipment to the semiconductor industry in producing tool sets that can produce features that are below 40 nanometers, which is basically right in the middle of this graph here. X-ray was a favorite for a long time in the 80s and early 90s in trying to look at X-ray technologies as a migration path to smaller features. In reality, the cost and the expense and difficulty of producing X-ray based lithography has basically pushed that trend to the side as laser based light sources have come on at much shorter wavelengths and have kept the industry pushing into these extreme ultraviolet ranges. But when we look at nanoscale technologies, we have to find a different type of technique to produce 10 nanometer features. The most prevalent method that has been utilized is single point E-beam or E-beam lithography techniques as far as producing features that are in the 20 nanometers or possibly even smaller range. I think the smallest I've seen documented is on the order of about 8 nanometers for lithography using electron beam. So we have a smaller set of technologies that allow us to look at these features below 40 nanometers. See essentially dip pen writing, we see ion beam milling, we see a few other techniques that are documented here. And I will later in the talk a little more about how we are addressing producing patterns and producing features at the sub 40 nanometer range. So how do these nanoscaled and quantum devices fit in with the grand scheme of things? Every couple of years, the International Technology Roadmap Organization produces a new roadmap, a new ITRS roadmap for the semiconductor industry, basically drawing on the expertise of some of the leaders in the field. And in the 2005 edition, they had a very nice graph which represented what they viewed as some of the more important categories associated with these devices. On the horizontal axis here is basically the speed of the devices, and this speed is projected on this side. The cost is projected along this back face. The cost of the technology based on the projections that they had, and then the size you can see projected on the bottom face. And if we look at where silicon CMOS-based technologies are, we see that the technologies have basically explored down to about the 10 to the minus 8 meter range, in that kind of 40, 30, 25 nanometer range, possibly even down to 10 nanometers. And we see where some of these other technologies lie, some of which we've talked about. We've talked about some biologically inspired technologies, molecular electronics. I'm going to be talking about some alternative quantum electronic devices, effectively SCT devices I'll talk about. And some of the work that's been discussed about carbon nanotube-based devices also would fall basically in some of these ranges. But what you'll note is that there are trade-offs in how these devices behave. And there's no one device that has either the smallest feature size, coupled with the fastest switching time, coupled with the least expense. So industry is probably going to get to a point where it finds niche areas for specific types of devices and specific types of uses of these different technologies. So I fully expect us to see over the course of the next 20 years the integration of SCT devices with molecular electronics, with biologically inspired devices, perhaps all on the same substrate in the same monolithically integrated package. I fully expect to see all of them for certain applications. So, because they all have different implications for how the device behaves, I think we also have to look at this hierarchical structure where we look at how the device behaves compared to the paradigm that we're currently in, and whether there are other paradigms that are necessary to allow us to go to the next state, whether it be with the techniques with quantum computing or soft computing, whether some of the spintronic or molecular devices will allow some unique contribution in those areas. That is not fully realized right now. So there's a lot of challenges. I think one of the major challenges is finding a way to have these devices interact with the microscale devices, and really that's related to the scalable operating conditions. A major issue with a lot of these ultra small devices is that either they do not conduct significant amount of charge, or they require a significantly large signal voltage in compared to the voltage out that they produce. And so the signal drive, whether it's a current or voltage drive, and whether we have the potential for amplification, which is one of the main drivers for producing a transistor, is that you can produce amplification or produce some sort of a switching result, is going to be a major issue in which of these types of devices finds utility and in what mode they find utility. It was brought up earlier in the conference that there's no paradigm right now for looking at how interconnect delays impact computing significantly, and I think that this also is something that we're going to see in a very different way at the quantum scale with these quantum devices. So I fully expect to see either direct integration or a heterogeneous integration of these devices to find some way to produce compatibility with existing microelectronic infrastructure. Because that infrastructure is not going away. That's an enormously valuable industry to the global economy. And that's an industry that wants to succeed and wants to find ways to keep itself going and keep itself thriving. So I'm sure that necessity is the mother of invention, and I'm sure that there will be ways that is borne out. So can we find ways to have both quantum and classical behavior merged into this integrated technology? Is it going to be easy for a classical device to interact with a device that maybe has multiple states, or maybe has to be measured with more than one state, which is very different than our binary system that we have with our typical digital electronics. So since we have no clear winner, I think it's very true that we'll have niche applications for these devices. We may find some in static memory, find some in non-volatile memory. We may find some looking at multi-level logic for very high complexity digital analysis or mathematical analysis. And we have lots of examples of that in our current technology set. Most of us have little pocket drives, little jump drives. The beauty of these devices is all because of flash memory. And flash memory can be embedded with other types of CMOS, but has a very specific and very high utility. We see that with DRAM. We see that with other types of devices that you may not be as familiar with. The long drain Mosfet is a device that's used for embedded power. And these devices have niche application areas. They're very important to the industry in those areas. And the scope of the microelectronics industry wouldn't be what it is without having these niche devices embedded. So I think we're going to see the same sort of thing happen with our quantum scale devices. And it all is going to have to come from this issue of coordination. So one of the ways that the faculty that are engaged in kind of this nanoscaled area at Michigan Tech have sought to seek that coordination is through the development of the Multiscale Technologies Institute. So I'm going to put on my associate director hat and do a little plug here. But basically, this institute was formed during 2006, but really came out of research that was initiated back in 2000 and in 2003, looking at technologies at the micro and nanoscale and trying to address issues that span the scales, where we were looking at technologies associated with molecular level and atomistic modeling devices, and figure out ways that these devices would be able to interact with the real world, because we certainly live in the real world even if we want to have devices that are at the nanoscale. So we've done that by providing a framework in which that we can conduct and promote interdisciplinary research. And we have roughly 35 faculty that are associated with this institute right now. Very diverse body of faculty, from chemistry to physics to all of the engineering disciplines that are engaged in our college and university. So this has been our effort to provide a framework from within which faculty at our university can engage in trying to address these questions and address the technologies that both impact the nanoscale, but also to find ways to practically apply the technologies and the science that's been developed into applications that will impact the real world. So some of the issues you've seen some of the technologies already represented through Dr. Yap's presentation and Dr. Pondy's presentation. There's a lot of work that's also done at the mesoscale, modeling and developing technologies. So what I'm going to focus on for the remainder of my talk is some work that we started in 2003, really effectively 2004, in developing technologies for producing room temperature single electron transistor devices. So we have a group, part of my group is looking at the underlying physics of the device, developing the technology, studying the implications of the design, and demonstrating technologies to produce these sub 40 nanometer features. And a lot of that focus has been right now on developing technologies surrounding the focused ion beam instrument that we acquired through this grant that started in 2003. So why single electron? There are several advantageous characteristics of these devices. They are three-terminal devices that, for the most part, mimic the behavior of field effect devices. That's not completely accurate, but if you think about a field effect device, you can glean most of the understanding that you need to get the understanding of how the SET device operates. Based on some of the technologies that developed, we can see that they are potentially monolithically integratable with existing microelectronic devices in a truly three-dimensional integration, meaning that we might be able to produce hundreds of layers of SETs, hundreds of sheets of SETs on top of existing platforms. There are several material systems that have been demonstrated to produce very effective room temperature capable SET devices, and both planar and non-planar configurations of these devices have been demonstrated. There are several challenges. A single electron has limited current and capacitance drive capability, so fan-out is potentially a major issue. The tunneling resistance for these devices is basically on the order of giga-ohms, and so at least for a room temperature capable device. And so the feasibility of coupling these devices back into microelectronics is something that requires significant interaction and understanding for how to actually build circuits of these devices that will be able to be used. Dot dimensions and configuration impact the behavior significantly, and the fabrication of suitably scaled features is difficult, certainly expensive with the direct write techniques that are available at these feature scales. So basically, the SET as a three-terminal has a source drain and a control gate, just like a FET does. The difference in behavior is that it utilizes either one or many isolated quantum dots to produce a tunneling current behavior that is controlled by this control gate. So the energy on the quantum dot is controlled by the gate, and the behavior of the device is characterized by unique, at least the current throughput is characterized by unique energy levels, as you would expect for quantum confined electrons on a quantum dot. The position of the gate matters. The device is configured. For planar devices, top gate, bottom gate, and side gates have all been considered. This is just a simple schematic of that side gate device, where the side gate provides a potential to the quantum dot. Because the coupling capacitances between the electrodes matter in these devices. You would like to have very small coupling capacitances, very low capacitances, for these devices to operate at speeds that are significant and operate at temperatures that are also significant. So functionally, if you were to draw a schematic of these devices, or to draw how they would be utilized, basically you have your source and drain terminals that are coupled to the quantum dot through a capacitance and a tunneling resistance, and you have a capacitively coupled gate that quantum dot to change the energetics of the dot. The tunneling rate is given by the energetic favorability of the available states, which is reflected by the energies across your tunneling barrier. This tunneling resistance represents the probability of tunneling across those barriers. And because we want to look at current flow, we want to look at both the tunneling probability both ways and the tunneling probability across both gates. There are some characteristic limits of how the device behaves. The charge and discharge time, or basically the switching time of the device, is related to that total capacitance of the device divided by the conductance of the device. And the limit on the conductance is based on the quantum limit of the material. Tunneling junction resistance is then also based on the available states that are available on both sides of the boundary. I think I'll move on past this because I think we want to get into more characteristics since then. A significant reference paper that was produced in 1999 from Konstantin Likarev is a very good survey paper on the fundamentals and the theory behind SET devices. SETs behave as a switch, as you would expect, based on the gate bias, modulating the region over which electrons can be transported across the barrier. And so they tend to have characteristics that look very much like this. Interestingly enough, this is also a characteristic that if you look at deep submicron field effect transistors, you also see a similar kind of behavior in those devices. So in the region around 0 is where you have this separation, where you basically have an off state or a near off state in the device behavior. So as I mentioned earlier, the favorability of tunneling depends upon the energetics of the conditions of the quantum dot with respect to the source and drain. And so the side gate or the gate electrode can change the potential on the quantum dot, allowing for a favorable transition to take place one way or the other way. These devices can be produced in a very in a fashion where it's a very reversible device. The source and drain can be reversed, or it is possible to make them look very one-sided by adjusting either the width or the barrier height from one side to the other between the source and drain of the device. Characteristic of these devices are regions at which current can significantly conduct and regions where current does not conduct. So you tend to see, as you adjust the gate voltage, you tend to see regions where you have spikes in current and other regions where you basically have nulls in the current, related to the energies of the available states. This is borne out in what's called Coulomb oscillations in the output drain current as a result of the sweeping the gate voltage for various drain source biases. This is an example of that for different conditions. This device in particular was measured at 77 Kelvin. And the characteristic widths and the characteristic heights of the current spikes that you see in the Coulomb oscillations is representative of the energies in the system. I think I'll choose to skip this for now. So there are some major challenges for producing these devices, for fabricating these devices. The most common method right now is E-beam direct lithography. This is capable of producing sub-40 nanometer features. It has been used for both the pattern and etch process, where a pattern is produced in photoresist and a feature in the underlying quantum dot and electrodes are produced by etching. It's been used for direct pre-decomposition of quantum dots and for producing both a vertical and lateral type devices. There are many methods for quantum dots. There's sputter or these spinner spray coating from a suspension. Some of these have already been discussed at this meeting. We have both the potential also for ultra-thin nucleation, where we have a droplet nucleation on the surface by evaporation or other methods, or direct decomposition techniques. So the limitations that we see is that E-beam lithography is not an easy technique to do large volumes of devices at once. So if we're looking at producing a 300 millimeter substrate with billions of transistors on it, it is not an array scalable device. It's or an array scalable technology. It's not something that you'd want to have to direct write for every wafer. It would be very time consuming and very expensive as a result. And we still have issues with feature control where our lines and spaces are not yet consistent because we're pushing the limits of these capabilities, these technologies. So we have, because of our acquisition of our focused ion beam tool, we've taken a look at that as a potential technique for producing a planar SET structure. So we've done some development on focused ion beam etching as well as deposition methods, and I'm going to present some of that hopefully relatively briefly to you. So a typical process flow would be to produce a suitable isolation, some sort of a substrate with something else, produce a appropriate material for electrons and quantum dots. In the case of the work that we have been pursuing, we've been looking at metallic dots and metallic electrodes. So we started out looking at the aluminum oxide and the nickel magnesium oxide systems. Focused ion beam tools basically are configured as scanning electron microscope systems are. You have a liquid metal ion source instead of an electron source that is extracted from the source through a high field. It's focused through a set of lenses down onto the sample. The beam sizes can be as small as 7 or 5 nanometers, which is a little bit larger than that for an electron beam because of the mass of the ions. Typically gallium is used as an ion source. They're accelerated on the order of 25 to 30 kilovolts before they reach the target surface. So when focused on the surface, they have the possibility of producing one of 4 different things. They can sputter etch the surface, they can produce heat in the substrate, they can implant themselves into the substrate, or they can be used to decompose a gas at or near the substrate. So in an etching condition, the ions, as they reach the surface, primarily serve to heat and sputter the material from the surface, and this is called ion milling technique that you may be familiar with. So another image of the column. This is actually our Hitachi FB2000 FIB that we utilize. This is configured also with a beam scanner that allows us to use direct CAD layouts for producing features on our substrate, and gives us a lot more beam control than the system as is. There are many modes that we can choose from very large apertures and high beam currents to very small apertures and small beam currents that can be used for different applications, whether milling or for deposition or for very fine resolution pattern milling, and some basic kind of common sense sort of things. The larger the beam size, the faster your processing, and the lower your resolution, as you would expect. So more detail of these modes, we see that we have a range of beam currents from tens of nanoamps down to a few picoamps. And so we have a very large range over which the process can be controlled for producing features at various scales. And we make very good use of that in the production of our features. So typically the beam is scanned in a raster arrangement based on the magnification that's been chosen and the beam size that's been chosen. The pixels that are magnified are determined by the magnification, the center-to-center distance, and the distance between the raster scans of the beam. And the dwell time defines basically how long the pixel maintains, or how long the beam stays at a particular pixel. The effort has been used to initially look what kind of minimum features can we produce. These were some features that were down in the 100 nanometer range for etching. We wanted to see, can we produce quantum dots by this method out of a single sheet of, or a continuous sheet of metal. And we've shown that yes, you can, but you're limited by, in the etch method, you're limited in the production of the dots based on the size. We found this somewhat troubling because we didn't really want a SET with a 40 nanometer quantum dot. We wanted an SET with a quantum dot that was significantly smaller, so that would be much more feasible to operate at room temperature. 40 nanometer dot basically can operate in the liquid nitrogen temperature range. So we developed this etch technique as far as we could to produce the actual 3-terminal structure, producing then a 40 nanometer quantum dot with basically a 10 nanometer tunnel junction, which is a very large tunnel junction, source, drain, and gate features by this focused ion beam milling. Well, it wasn't an ideal structure, but we wanted to see what it would do. So we actually did some initial test results or some initial testing on this device, and determined that yes, we did have isolation. We were getting some unusual behavior from our conductance curve. Looks like a straight line. It's not exactly a straight line near zero gate potential. What we saw that as our tunnel junction resistance was significantly smaller than our quantum resistance, just based on the thermal energies of the electrons. So we didn't see any Coulomb oscillations with this initial device because we had such a large quantum dot. But it did allow us to look at some initial behavior of the device, and allowed us to pursue an alternative path. I'm going to skip this for the time being. An alternative path where we wanted to understand what were the limitations of the process technology, what were the limitations of the beam etching. The focused ion beam has an error function profile near its tip with a Gaussian tail. And this is a profile that has been characterized really over the last decade by the manufacturers as well as by several researchers around the world. That profile results in a significant amount of energy and a significant dose of ions that extend far beyond the nominal full width half max feature profile, which is what is stated. So we wanted to look at how small can we actually go with this technology, and what are the implications of doing this etch. So we played with the parameters of our tool, and looking at a circular rastering pattern, which was required to produce an isolated dot. We wanted to look at how much energy was being imparted to the region inside this raster scan, to try and understand both in terms of material properties and in terms of how much energy was being applied to the dot as opposed to the region where we wanted to have the sputter etching take place. So we did a series of models to look at how the energy overlap behaves as you bring that circular raster scan closer. And we see that at 40 nanometers we have minimal energy being applied to the central region of the dot. But as we get to smaller regions, 20 nanometers for instance, which would be a very nice size, this would produce on the order of a 12 to 10 nanometer quantum dot. We see that roughly 60 to 80% of the energy that we see at the peak of the beam is being applied to the center of the dot as well. And obviously as you get closer, that becomes even more of a problem, where basically you're overlaying your beam right on itself. And we see that we have really a functional limit in terms of how much or how close in proximity we can produce features. And we've seen this through other experimental evidence that the amount of energy that's applied to the regions that we don't want to etch becomes significant at sizes below 30 nanometers, even for the smallest beam size that we can produce. We did some analysis of this based on the dose and the accelerating voltage and the radius of our raster scan, and we found that for I believe it's a 30 nanometer radius, we were seeing temperatures on the order of 600 degrees C locally where that dot was being produced. So just some examples or some demonstrations of how this was done. We see at 50 and 45 nanometers that we can still produce quantum dots, but then at the dimensions below 30 nanometers, especially in aluminum, which is a lower temperature material, we're seeing this causing a problem. So we thought, okay, we're not going to be able to get our 1 to 10 nanometer quantum dots by etching. We're going to have to come up with another technique. Well, fortunately, we also are able to do deposition with our tool, and we actually have a tungsten gas source, a tungsten precursor source for producing tungsten thin films by fib. And we thought, okay, we're going to see, can we produce isolated islands of tungsten by fib deposition? And so we wanted to look at controlling the island formation. And we found that actually by controlling our residence time, we are able to produce isolated islands on the order of 10 nanometers or smaller because of the trade-off in the deposition rate versus the sputter ablation rate caused by the fib beam. So we were able to produce then islands. I think one of my slides is missing here. Huh, okay, sorry, I'm missing a very important slide, but I'll show it to you here. Able to produce isolated islands in a matrix that range from basically 15 down to about 6 or 5. And this we can do very repeatedly, very controllably. And we're using this then as our source for our quantum dots for our SET devices. Now we have looked at basically a new technology utilizing the deposition mode for producing the quantum dots, and then using deposition also for producing the leads into the device. So we're looking at here, instead of a single dot device, we're looking at a multi-dot SET, which changes its behavior somewhat. But I'll show you some results on these devices next. So we found that this technique works very well. We have a technique for oxidizing the quantum dots that is not yet published, so I'm not going to talk, and actually I'm not authorized to talk about it yet. So, but this device we're able to produce on the order of 50 nanometer spacing between our source and drain electrodes, which means we probably have on the order of 3 to 5 quantum dots minimum that are participating in conduction in the device. And we see that, as we saw with the reference source, we see that about the zero gate potential and zero drain potential, we see curvature in our conductance, and that's indicative of this quantum behavior in the SET. And that is confirmed even further as we look at small scan across gate voltage, and we see this behavior of Coulomb blockade taking place in our drain current for a given source drain voltage. And this was measured at room temperature, and we do have measurements that have also been taken at lower temperature to look at comparing and trying to understand the behavior of the devices. Another graph over a slightly different range, I believe also at room temperature. Anyway, so for the various topologies we've looked at these results, and we do have confirmation in these outputs, confirmation that we are indeed seeing these Coulomb blockade events and quantum confinement results in the outputs. Again, various device topologies give slightly different behaviors. We see in this case, we see much stronger curvature at the extremes of the conductance curve, which is potentially a good thing. And we see this for a variety of different devices, spacings, and configurations. So we have confirmation that, yes, we do see room temperature SET behavior. And to our knowledge, this is the only, we are the 5th group in the world that's demonstrated room temperature SET behavior. There's only one other group in the US that's done it. So there's not, this field has been around for 10, 15 years. These sorts of devices have been proposed much earlier than that, but effectively have been studied for the last 10 to 15 years. The first demonstration was in the late 80s and some demonstrations in the late 90s. But there haven't been any other recent demonstrations, and certainly not with this system or by this method. So we see from these results, we see that we have tunneling resistances that are on the order of tens of gigaohms. This is very good for room temperature operation. It's in a range that's very appropriate. And when we also see then drain source capacitances, which is one of these key capacitances, that for different device configurations we see very small capacitances on the order of a tenth or smaller of an attofarad, which basically means that we're looking at very small numbers of electrons in these systems, which is very good. So, where do we go from here? Yes, we have a multi-dot quantum SET device that works at room temperature. We are looking very seriously at expanding our modeling. I have a new doctoral student that has started with me this year to fully correlate the tunneling probabilities and potential parallel paths, as well as trying to look at the impacts of the actual dot behavior as well. And we are actively exploring alternatives to our fib for area patterning, because that, as I mentioned, is one of the key issues with all of these technologies. How do we produce these devices over a large area without requiring hours and hours of electron beam lithography time? We're exploring the SET as an electrometer transduction platform for bio-inspired sensing. We have an active effort in that area. That's actually where the initial SET effort came out of, and we are currently engaging with Freescale Semiconductor and with IBM Corporation, looking at integrating these SET devices directly within CMOS. So fib is not easily scaled to large scales, and we do need to address this, and we're looking at, another one of my doctoral students is very actively looking at ultraviolet nano imprint lithography as an array writing technique that will allow us to get into that 10 to 20 nanometer range in the near future. We're looking at that in probably the next 18 months. So can we use these? These devices have been demonstrated to be useful in reading out quantum dots, so they may have application in QCA logic and QCA memory. They have also been used as electrometers. That's basically how they've been used with the QCAs as well. They're very sensitive single electron electrometers, and they've been used in measuring ultrasensitive, used for sensing applications for ultrasensitive measurements, basically single molecule kind of sensing. And coupling to the charge in a qubit is another way that's been considered and I think theorized. I believe this is a theoretical paper. So there are ways that this can be used to directly integrate quantum computing with these sorts of quantum electronic devices, and ultimately, hopefully, we will see this merger in the long term of the merger of these quantum scale devices with our microscale and out to our macroscale world. At room temperature too, which is what everybody wants. So I appreciate your time, and I appreciate you staying here before lunch. I wanted to represent this rather large group. My colleagues in my department call this my Indian battalion, because most of the students that I have that are working on my quantum scale work are actually Indian or Asian. And our collaborators at the Army Research Lab and the sponsorship through DARPA with through the U.S. Army Research Lab. So, do you have any questions? I'll leave you with a picture of our institution.
You showed a slide in the beginning which showed the various process nodes like 120, 90, 65. So one of the reasons the industry still makes most chips at 90 nanometer and not 65 is that you can't design a chip which contains like 100 million gates.
Mm-hmm.
So potentially, even if today we could make a chip with a nanometer scale which could potentially have 1 billion gates, it would not be of much use because you can't make a chip with 1 billion gates. So is any work
not yet. Not yet.
So is any work going on in this direction as to how you could make a chip with so many devices which would utilize a nanoscale chip?
Well, I think some of the ways that industry has looked at embedding some of these non-traditional devices, there has been, I think, significant interest in how could we utilize these devices for embedded memory. And if you can embed the memory basically above the electronic substrate, who doesn't want a gigabit of static memory or non-volatile memory on their processor? I mean, right now, yeah, the Itanium, the dual-core Itanium processor has what, 300 million transistors on it, or is it over that, 300 or 400 million transistors? Basically, I think a third of that chip is dedicated to onboard memory for the cache memory on the chip, and I'm sure that Intel would be very happy to find ways to get rid of that, of some volume of that cache memory on that very expensive silicon real estate, if they could put it up in their inner level dielectrics or stack dozens of layers of these in their dielectric stack. Because that's a very easy part of the process. Once you get to the back end part of a CMOS process, you can basically keep going in producing metal and dielectric layers. Maybe not quite to infinity, but you can produce an awful lot of layers that don't always get utilized. So I think that one of the ways that we may see these really function, SETs initially may be utilized as very effective electrometers for measuring data in and out of a static or a non-volatile memory cell. That may be one way that they're utilized very immediately. I don't completely agree with you. I know your background from our conversations earlier in the week, but I don't completely agree with you that the industry doesn't want to produce chips that are more than 300 to 500 or 300 to 500 million transistors. I think the industry wants to solve the computing needs that it has applications for, and it sees bottlenecks. For instance, heat dissipation is one of the biggest bottlenecks that it sees. But it sees bottlenecks in its technology that it can't go beyond currently. And as we see with FETs, as we go to smaller and smaller gate lengths, we have higher and higher leakage currents, which means we have more and more static power dissipation that's just lost. It's just wasted power. And so another way that this may help is that if these devices basically have a low off-state leakage, which most of the quantum devices do, provided we can work out the fan-out issues with these very high impedance inputs and very high impedance outputs, I think any possibility of reducing that overall leakage current and therefore reducing the static temperature of the chips, I think all of us would appreciate that. My Mac has a dual-core Pentium or dual-core processor in it, and the heat is sunk right to the titanium case, and let me tell you, that thing gets really hot. So I think all of us would appreciate having a little less heat and a little more battery lifetime and a little more potentially more power out of the chips.